Here on Earth, we measure our lives in familiar units. We drive to the store in miles, we track our flights in kilometers, and we manage our trips in hours. These numbers make intuitive sense. They give us a feeling of mastery over our environment. But the moment we look up into space, that logical framework collapses. To reach our closest celestial neighbor, the Moon, you would have to drive a car at a constant highway speed of 100 kilometers per hour, non-stop, for over 160 days. And once you cross that vast expanse of nothingness, looking back reveals a fragile, isolated blue sphere cradled in a black void. Pushing further out, even our fastest commercial jets become practically stationary. If you boarded a flight traveling at 900 kilometers per hour, it would take you 19 years to reach the Sun, and upwards of 50 years to reach Mars when it's on the opposite side of our solar system. That massive, constantly shifting distance between Earth and Mars turns robotic space exploration into a logistical nightmare. Every rover or probe we send faces a journey fraught with complex orbital dynamics just to hit a moving target. Kilometers and miles lose all practicality out here. To even begin comprehending our own solar neighborhood, astronomers had to invent an entirely new yardstick. This scale model illustrates the gap between Earth and the Sun, 150 million kilometers, or 1 astronomical unit. It serves as our new yardstick. Even light, traveling at 300,000 kilometers per second, takes 8 minutes and 20 seconds to cross that single AU. Applying this scale to the edge of our planetary neighborhood, it takes that same light over 4 hours to reach the ice giant Neptune. We have managed to send physical objects out into this expanse. Launched in 1977, the Voyager 1 space probe has traveled for over 4 decades, covering more than 22 billion kilometers to become the farthest human-made object from our planet. In 1990, astronomer Carl Sagan requested we command Voyager to look back at us from 6 billion kilometers away. That single command resulted in the iconic pale blue dot image, capturing Earth as a tiny, faint speck in the dark. Yet, despite traveling at roughly 17 kilometers per second for nearly half a century, Voyager 1 is only just crossing the threshold of interstellar space. On a cosmic scale, our physical reach is effectively zero. At the fringes of our solar system lies the theoretical Oort Cloud. Once we hit this icy boundary, counting in astronomical units becomes completely impractical. We need a third yardstick, the light year, which is the distance light travels in 1 Earth year. Our nearest neighboring star system, Alpha Centauri, sits about 4.4 light-years away. To put that distance in perspective, our Voyager spacecraft would need over 70,000 years to reach it. Now apply that yardstick to our home galaxy. The Milky Way spans roughly 100,000 light-years in diameter, containing hundreds of billions of stars, each potentially hosting their own planetary systems. This diagram maps out a tiny sphere known as the human radio bubble against the backdrop of our massive galaxy. Extending roughly 100 light-years from Earth, this microscopic circle marks the absolute furthest extent of our electromagnetic footprint. Every radio and television signal humanity has ever broadcast out into space lives inside that boundary. Our earliest transmissions are only just now forming the very edge of this expanding, invisible sphere. If you step beyond that tiny 100 light-year bubble, our entire recorded history disappears. To the vast majority of civilizations that might exist in the Milky Way, we are completely undetectable. Leaving the Milky Way means entering the silent expanse of intergalactic space. Here, the gaps between galaxies are so immense that counting in single light-years is useless. We have to start measuring in the millions. Our galaxy belongs to a cosmic neighborhood known as the Local Group, containing over 50 clustered galaxies. Light takes 10 million years just to travel from one end of this local assembly to the other. Stepping further back into the cosmic ocean reveals the Virgo Supercluster, a massive collection containing thousands of galaxies scattered across a region roughly 110 million light-years in diameter. Finally, we arrive at our ultimate macro home, Laniakea. This gravitational structure spans 500 million light-years and contains the mass of 100 million billion suns. Inside this sweeping web of motion and attraction, our entire galactic history is reduced to a microscopic speck. We reside deep within a gravitational masterpiece that dwarfs anything our minds can intuitively grasp. This massive sphere represents the absolute physical limit of our vision, the edge of the observable universe. With Earth at the very center, the boundary of what we can theoretically detect stretches an astonishing 93 billion light-years in diameter. But this creates a fascinating numerical paradox. If the universe itself is only 13.8 billion years old, how can we possibly see a span of space that is 93 billion light-years across? The answer lies in cosmic expansion. Ever since the Big Bang, the space between celestial bodies hasn't been static. The black void itself is actively stretching like elastic, pushing galaxies further and further apart. That expansion leads to a staggering physical reality. Because the universe is constantly ballooning outward, the regions of space at the very edge of our vision are moving away from us faster than the speed of light. Because the light from those distant regions can never reach us, our ultimate yardstick is permanently broken. The true size of the entire universe remains entirely unknown. We are left inside an infinite cosmic library, watching helplessly as countless stories retreat forever into the expanding dark.